Hi, my name is Ramon Gomes da Silva. I am a PhD student at Pontifical Catholic University of Paraná, PUC-PR, and I will present you the paper entitled Wind Energy Multi-Step Ahead Forecast based on variational mode decomposition. The agenda of this presentation is the introduction, a brief description of the dataset, a methodology, some results, a conclusion, and the acknowledgments at the end of the presentation. So, wind energy has been increasing its operation in the energy matrix in the last decades in many countries around the world. Even in Brazil, whose electrical power system is majority composed by hydroelectric systems, the wind energy already has a great parcel of the national energy matrix. So, in Brazil, the wind energy generation supplies around 88 million people and represents 70% of the energy consumed in the national interconnected system. So, wind energy is classified as an intermittent source, mostly due to non-linear behavior and its fluctuations. So, to forecast wind energy with some accuracy is becoming challenging due to its fluctuations. So, variational mode decomposition, we're gonna call VMD, can handle with the time series, which presents higher fluctuations. Also, diverse artificial intelligence (AI) models for multi-step ahead forecasting can help to forecast the wind energy as accurately as possible. So the objective of this paper is to develop a decomposition framework for wind energy forecasting multi-step ahead, which means for 30 minutes, 1 hour, and 2 hours ahead. So the proposed model is composed by VMD and some AI approaches, which they are different for each other. So we're gonna call heterogeneous AI approaches. So the dataset comprises the days 23rd, 24th, and 26th of August 2017, respectively. As we can see at the right of the figure 2, so the dataset 1, 2, and 3, respectively. For each one of the datasets, there are 144 samples, and the samples are for each 10 minutes observation. In table 1, the output and the inputs of the systems are described. So we have the power system as an output, the both generator bearing temperature, the generator speeder, wind speed, absolute wind direction, nacelle direction, and ambient temperature. Those last are the inputs of the system. So the methodology used basically 4 approaches: the VMD, the BRNN, SVR, and QBIST. So the VMD decomposes the data into 5 different components. We're gonna call IMF 1 until 5. So 3 different algorithms are used: BRNN, which are Bayesian recurrent neural network, QBIST regression, SVR, which are support vector regression with linear kernel, and both all the components are trained by each of the algorithms, and they are integrated at the end of the training phase. So by a simple summation, generating 3 different models: VMD BRNN, VMD QBIST, and VMD SVR. And these 3 models are evaluated using relative roots mean square error and symmetric mean absolute percentage error. So these are the performance metrics used in this paper. So as you can see in the table 2, there are described each of the datasets for each models for each forecasting horizon 3, 6, and 12 steps ahead. So in bold, VMD Cubist reached the best forecasting error, the lower error forecasting for each one of the models. So VMD Cubist is the most suitable model for wind energy forecasting. As you can see, the minimum that the model reached was 2.34% of the error. Here the plots for each dataset 1, 2, and 3 with the observed in a blue line, and the red line is the predicted model, which means the VMD Cubist model predicting. So we can see that the model could learn both the behavior and the pattern of the data, giving us an accurate model, an accurate forecasting for these datasets. So as a conclusion, this study proposed a decomposition model by using VMD and AI models to forecast wind energy multi-step ahead. The VMD was coupled with BRNN Cubist and SVR as forecast models, and indeed, the VMD Cubist approach had a better performance than compared models in all forecasting horizons. For feature works, couple stacking ensemble learning approach is an option, adopting different signal decomposition approaches, and optimizing the hyperparameters of the forecasting model by using multi-step objective optimization. Some acknowledgments. We want to thank CAPES, CNPq, Fundação Araucária, and PUC-PR for support financially this work to happen. So thank you already for watching this presentation. If you have any question, leave the comments below, and I will answer as soon as possible. Thank you again. Bye bye.